So my name is Judith Verstegen. I'm from the Institute for Geoinformatics, University of Münster. And my co-author is Kai-Ivar van der Wijst from Utrecht University. The topic of our talk today is statistical analysis of model ensembles for policy support. So the use of models to support policymaking has become relatively common, as for example demonstrated by the fact that there is this session. For many policy-related questions, integrated assessment models are used. Now, these models are called integrated because they basically consist of a set of many different models that together model the human system coupled to the Earth system. In the human system, there are different drivers, for example, the population, the economy, and the state of technology. And any change in these drivers over time makes that there is a change in demand for resources and also the use of these resources. The main resources that are modeled in there are the energy and the agricultural resources. The change in the use of these resources has an effect on the Earth system, for example, on ecosystems, as well as on climate change. And then there is a feedback loop back to the human system because climate change obviously has an impact on the human system. So this very shortly about integrated assessment models. There isn't one particular integrated assessment models, but there are different ones for two main reasons. First of all, this very complex system of the Earth and the human system integrated, obviously our understanding of that system is incomplete. So different models have a different interpretation of these systems and therefore the models, they differ. On the other hand, models are always an abstraction of the real world system, and how you abstract the real world system depends on the question at hand, so that is basically the focus of the model. So because of that, we have a set of integrated assessment models, and when we run them together, they can be seen as a representation of different descriptions, different possible descriptions of this coupled system. Then there are two other dimensions of uncertainty there, and these two dimensions are captured with scenarios. On the one hand, there is uncertainty in how the drivers in the human system will develop over time. And this uncertainty is captured usually in pathways, this socioeconomic pathways, also called SSP scenarios. And these prescribe different assumptions on economic development, population growth, geopolitical stability, etc. Then we have the RCPs. These are the scenarios that depict different climate targets. And in the newest set of scenarios, these range from RCP 1.9, that is representative for the 1.5 degree target, to RCP 6 and higher, that basically imply that there is no climate policy implemented. So these three aspects together make that there is a very large spread within scenarios caused by the different integrated assessment models, as well as between resulting scenarios. The usage of these ranges is, in our opinion, rather limited at the moment. So many studies mainly use the median or mean of this range and or the minimum and maximum. Here you see an example of a figure from the IPCC report, where it's indicated what the annual greenhouse gas emissions are over time under different RCPs. And you see depicted here, for example, in gray, the range between the 10th and 90th percentile, which is a similar thing as the minimum and maximum, as well as with the dotted line here, the mean or the median. And earlier this morning, it was very nicely phrased by Joseph Guillaume in another session that there is a risk that this uncertainty is used as an excuse for inaction if we don't translate it to something that is more understandable. So we argue here that statistical methods can be applied to multimodal ensemble results to translate this output uncertainty to simple policy relevant information. As an example, we answer in this presentation two different questions, one related to uncertainty within scenarios and one related to uncertainty between scenarios. The first question is, how certain can we be that a scenario is below a particular emission or cost limit in a certain year? And the second one is, are the differences between scenarios significant given the uncertainty in the model ensemble? In this picture here above, the first question would be related, for example, to the red line over here, and whether we can be sure that the scenario results depicted here are above or below that line. In the second question, it's more about the differences between scenarios. So the question would be, for example, is the difference between the range in light blue and the range in dark blue actually significant given the uncertainty? We use as a data set all model runs from the RCP 1.9 for the scenarios SSP1 and SSP2 from the SSP database. Based on that query, 10 model runs were selected from the database that you see depicted here. The 10 model runs come from 6 different integrated assessment models, and 6 of them are for SSP1 and 4 of them are for SSP2. To better understand our methods, I'm now going to change the visualization of these model results into box plots. As you see here, so now I've grouped everything on the previous slide based per scenario. So in blue, you see as a box plots all model results for SSP1 from the different models, and in yellow for SSP2, and the groups are done per year with a time step of 10 years. To answer the first question, we can use the concept of exceedance probabilities. Exceedance probabilities help to identify to what extent one can be sure that a threshold is or isn't crossed, given a data sample. If your data sample is, for example, the one depicted by this distribution over here, with a mean of -2 and a standard deviation of 0.5, then the first thing you have to do to compute an exceedance probability is to translate that to a cumulative distribution as shown here on the right. Then you can answer the question, for example, what is the probability that x is above -1? To answer that, you go to the x-axis to -1, you read what the value is of the green line, and it appears to be 95%. That means that you have 95% certainty that the value is below -1, and therefore 5% is your exceedance probability. We can apply this concept to the model ensemble when we see that model ensemble as our sample. So applied to the selection of scenarios from the SSP database, we can make this figure where we have the threshold of 0 emissions to evaluate. And when we evaluate this threshold, we can see, we can color the box plots. So in red, you see all model ensemble results that are definitely above this threshold. And with definitely in this case, I mean at least 95% sure. In green, we see all the ones that are definitely below. And in orange, we see only one box plot for which this question cannot be answered. In other words, it is indistinguishable whether it's above or below the threshold. This is quite a positive result, I would say, because this particular question about the threshold, the uncertainty in our model ensemble, it doesn't really affect. So many of the cases are either red or green. That means that, yeah, we can still answer the question despite the uncertainty in the model ensemble. As a second method, I use significance tests. The general idea of a significance test is to evaluate the likelihood of some claim about one or more populations given a data sample from these populations. In this case, we can see our ensemble of model results as a sample from one or more populations. For our example, I used a Welsh ANOVA. The idea of an ANOVA is that you can test whether when you have a certain large sample and you think that there are groups in that sample, whether that is likely or not that it's true. And an ANOVA works in a way that it simply checks whether the distances over here between the means of the presumed groups are much larger than the means, the spread, so the variance within the groups. And if that difference is large, then it's likely that at least one of the groups has a different mean than the others. Applying this to our selected scenarios, we can make this figure. Here I test each time 1 by 1 per year the difference between SSP1 and SSP2. And if that difference is significant, I've placed a star. We see that only in 3 particular years, 2020, 2030, and 2070, the difference between the two SSPs, between the two pathways, is actually significant. So in this case, the uncertainty in our model ensemble has a much larger effect. It makes that there isn't a real difference, or not a significant difference anymore, between the pathways that are taken when we have different socioeconomic conditions. I must say, however, that the significance applies only to this particular variable that we have here on the y-axis, that is yearly emissions. So of course there may be differences between the two scenarios in other years for other variables. To summarize, I've told you, you probably already knew, that models are always abstractions of reality. Because of that, model outputs will always be uncertain to some extent. Therefore, we encourage modelers to quantify uncertainty in their models. And we hope to convince policymakers that uncertainty shouldn't be seen as daunting, but instead can be seen as additional information that can be used to answer straightforward questions. To come from uncertainty to this additional information, we have shown here 2 methods, exceedance probabilities and significance test, but there can of course be other methods. I thank you very much for your attention. I would be interested to receive any questions, either related to my talk, but also questions that you think could potentially be answered with these methods. Thanks.
Thanks, Judith. Are there any questions? We've got some time. So I've got one. So one issue with the example you've shown is with the scenarios. How can we know what the distribution is that's actually being formed there? So for example, if we only have a sample of 5 models and ensemble of convenience, I suppose.
You mean that you don't know what the probability distribution is, but you don't know the probability function, but only the distribution. Is that your question?
Sorry, I guess I understood that what you're doing was taking the scenarios and from that calculating an exceedance probability. Mm-hmm. But if we don't know that those scenarios fully sample the space, is that an issue? Yeah, you're absolutely right. So of course the scenarios don't cover the whole potential space of potential emissions, but that is a problem, I would say, that is also already present when you just take the minimum and maximum. So in my opinion, isn't a problem new to the methods that I apply, but it was there before when you were just computing the mean. But yeah, we have to always state that the models are representative for a range of potential conceptualizations of the system, but there are other potential conceptualizations that are not captured by any model. True.
Are there other questions from the participants?
Sorry, may I ask a question?
Yes, sure.
Following the previous question, I wanted to ask, given the fact that you don't know what is the distribution, what are your assumptions? For example, normal distribution among the scenarios, or something else probably?
Yeah, so given the model ensemble that I do have, I checked whether the annual greenhouse gas emissions were normally distributed, and they were not. So that's why I use a Welsh ANOVA instead of a regular ANOVA that doesn't have this assumption of normality behind it.
Thank you.
Other questions? Okay, thanks a lot for your presentation, Judith. I think that made very important points. Very important takeaway message is that we should not be afraid of uncertainties. This is what we need to, and policymakers need not to be afraid of that. And I think you really made a point for that and also showed very intuitively how that can be communicated. So thanks a lot for your contribution to this session, which is indeed very rich and touches precisely upon many of the aspects which are relevant for the use of models for policy support.